AFL mainly mutates the seed in the following two stages, which are deterministic stage and Havoc stages. And to be more precise, it consists of three stages, including namely the splicing stage. But I will omit this splicing stage as it is only turned on when the previous these two stages, deterministic stage and Havoc stage, totally fail to generate interesting input. And it doesn't happen often when testing real-world programs. So let's focus on these first two stages. The first deterministic stage has no randomness in the process of generating mutants. And Havoc stage steps generate the mutants depending on a huge amount of randomness. So let's look at this stage one by one. The first stage is to generate mutant by using only a single mutation operators, thereby pursuing small change to the original seed. Conversely, the second stage favors big change to the seed inputs by using multiple operators simultaneously. Okay, I will explain the first stage in detail. In this deterministic stages, it applies the predefined mutation operator to the original input from the start to the end. So there exist multiple predefined operators in AFL, such as 1-bit flip or 2-byte flip, or arithmetic increase or decrease, and so on. So for example, let's apply 1-bit flip operator to this original seed input. So it generates the first mutant by flipping the first bit of the original input from 1 to 0 in this case. And likewise, the second mutant will be also generated by flipping the second bit of the original state. And in this way, starting from the first bit, AFL will generate 8 mutants by flipping each bit of input in orders. For another example, if we are applying 2-bit flip operator to this input, the first mutant will be generated by flipping first 2 bits of the original seed from 1, 0 to 0, 1. Likewise, applying this operator to the original seed in order. In this case, AFL will generate 7 mutants where the last mutant will differ from the original input only in the last 2 bits. So in this way, during the deterministic stages, it sequentially applies each mutation operator to the input from the start to the end. For example, suppose that this table shows all the predefined mutation operators of AFL, and AFL takes the selected seed as 1 and first applies the 1-bit flip operators and apply the second operator 2-bit flip and applies 4-bit flip operators. In this way, after applying all mutation operators in order, AFL finally ends the deterministic stages. So that is, this stage focused on a slight change of the original input by using predefined mutation operators. Okay, let's move on to the next stage, Havoc stages. In Havoc stage, AFL aims to apply multiple operators to mutate the seed inputs. So in this stage, it takes the original seed as 1 as input and it first determines the number of mutants to generate. Suppose that the number is just m. Then while generating m mutants, AFL also decides to how many mutation operators to apply for each mutant simultaneously. So suppose that the number of operators for generating the first mutant is n. Then it iteratively chooses which operator to apply and where each operator is applied respectively n times, and then generate the first mutant. So let's see the simple example for Havoc stages. So suppose that the number of operators to mutate the original seed is randomly selected as 3. And also the first operators and each location to apply is also determined randomly as just like 4-bit flip and the 3rd bit position respectively. So after applying the first random operators, and the original seed will change from 0, 1, 1, 1 to 1, 0, 0, 0, which is 4-bit flip result starting from the 3rd positions. And the second operator is also randomly selected as insert operator in this case, where these inserted values are also determined as 0, 0 randomly. And let's apply this insert operator to the input to which the first operator has been already applied. So the size of the mutant input will increase by 2 bits. So total it will be 10 bits. Then let's apply the third operator delete, which 1 bit size at the location 7 bit. So then finally we generate a single mutant 1 M1 generated by in Havoc stages. So as you can notice, all the text highlighted in green denotes the randomness of Havoc stages, which is including the kinds of operators and the values or size related to each operator and the location to apply to operator and so on. So again, say Havoc stage totally relies on randomness to generate mutant. For example, it randomly decides how many mutants to generate for a given seed input and how many operators to apply and what kinds of operators to apply and where to apply to the operators and so on. So if considering the realistic input such as 3 megabyte MP3 files, this decision making in Havoc stage induces tremendous search space. So far, we learned 2 stages of AFL for seed mutations. So here is my simple questions. So which stage do you think is more effective at finding bugs? Small change to seed input but determining stages, or big change but purely random Havoc stages? I will give a 10 seconds to think. So which one is more effective at finding bugs? Actually, in my brief personal experience, of course, I also have not studied gray box testing in depth, but Havoc stage is much more effective than determining stages based on my personal experience. So if you are watching my lecture so far, you can get a rough idea of what the important research topics for this mutation-based fudging are. Yes, the first topic is about automatically generating effective seed pools. As I already mentioned in these lectures, the key assumption of mutation-based fudger is that it takes valid seeds or well-structured seeds as inputs. That is, the effectiveness of mutation-based fudger heavily depends on the quality of the initial seed pools. The second important topic is about seed selections. This mutation-based fudger like AFL usually takes a seed pool which consists of 100 or 10,000 valid seed inputs as inputs. So moreover, AFL continuously adds this interesting input into the seed pool during the testing. So selecting the promising seeds first that are likely to find bugs or maximize code coverages is an important part of the mutation-based fudgers. Hence, many seed selection strategies such as AFL best have been presented in these literatures. Lastly, as we expected, the third topic is about seed mutation strategies, which determines how to mutate the given seeds. So many mutation strategies such as MOPT have been also presented a lot in these research areas. And each topic is an active research topic in the fudging domain to date. Okay, let's sum up these lectures. Today, we have learned about the gray box testing, which is classified into the major techniques, mutation-based fudging and generation-based fudgings. In particular, we focused on learning the mutation-based fudging, having three components: seed pool generation and seed selections and seed mutations. And seed mutation is consists of deterministic stage and Havoc stages as well. Okay, this is the end of this lecture. So see you next week. Bye, everyone.